So, photoelectric effect or dual nature of radiation and matter, important question, part 2. Which of the following wavelength or wavelength, there can be all of them or few of them or one of them or none of them, can be able to eject photoelectron from a metal surface of phi equal to 4 electron volt. So there are 3 wavelengths given here. Now, what we can do, we can find threshold wavelength associated with this work function, or else we can also find energy associated with these wavelengths. Two ways we have to answer this question. So it is better to find one value and then compare it with others. So here we have 4 phi equal to 4 electron volt. So phi, we know hc by lambda, and because it is related to stop that work function, so we put 0 here. It is threshold wavelength equal to 4 electron volt. Keep this thing in mind that it is in electron volt. Now hc, value of hc, we know the value of h, we know the value of c, but together hc comes out to be 1.989 into 10 to the power minus 25 joule meter. Why is it so? Joule second, and here meter per second, so per second and second will get cancelled, so joule meter. Or the same value in electron volt is 1.242 into 10 to the power minus 6 electron volt meter. So might it would be given or not, both things can happen. So let us suppose this is given, or in fact it is not given, h is given separately and c is given separately. So we can find hc separately and then we can put the value here, but it is better to memorize these, practice a lot, then you could be easily memorize these values. Well, so I'm doing it sidewise and putting directly value here. So it is, hc is 1.242 into 10 to the power minus 6 upon lambda, so I'm putting upon 4 and taking lambda naught here. So lambda naught will be now 0.3105. We will divide simply 10 to the power minus 6, and this is in case we want to convert, it is in meter, we want to convert it into nanometer, then we have to multiply it. See what will happen. It is a tricky way to do that. I'm doing it here. Lambda naught, it is 0.3105 into 10 to the power minus 6 into 10 to the power 9 nanometer. Nanometer means 10 to the power minus 9, and this is 10 to the power 9. So we know that 1 meter is equal to 10 to the power 9 nanometer. So that is what we have done it here. And now it will be 0.3105 into 10 to the power 3 nanometer. And we can adjust decimal, 310.5 nanometer. So what is the definition of threshold wavelength? It is the maximum definition, or maximum wavelength above which photoelectric effect does not take place. So all the wavelengths which are above this could not be able to eject electron. So lambda naught is greater than lambda a, because for wavelength case is reversed. So it means lambda a for this thing. So a, that is 200 nanometer, will be able to eject electron, and whereas lambda naught is less than lambda b, and also lambda naught is less than lambda c. Or in other way we can say lambda b is greater than lambda naught, lambda c is greater than lambda naught, so they are not able to eject electron. I repeat, if frequency would be given, then we would find the frequencies which are greater than threshold frequency, but for wavelength we go on the other side and we see that the wavelength which are less than threshold frequency could be able to eject electron. Next, Which of the following metal or metals release photoelectron when photon of wavelength this fall on it? Here again a trick. We should not go for them separately. We can do it trickily by finding energy associated with this photon. So if its energy is greater than any one of them, or all of them, or few of them, so only from those metals electron could be ejected. So we will find E equal to hc by lambda, and see, it is once again hc as discussed earlier. So also this value 1.242 into 10 to the power minus 6 electron volt meter, it can also be given in terms of nanometer. So if we convert, if it is not given, it is given in terms of electron volt meter and not in nanometer. So in fact we can find it out. How? As we did earlier. So 1.242 into 10 to the power minus 6 electron volt into 10 to the power 9 nanometer. So it will be 1.242 into 10 to the power 3 electron volt nanometer. So using this, we can directly put the value here, 1.242 into 10 to the power 3 electron volt nanometer upon wavelength is 666 nanometer. Nanometer will get cancelled. Now the biggest trouble, it is very difficult to divide it. We can, but is there any shortcut? Yeah, 666, its double will be 13 something something. So the answer must be 1.9 something. In fact 1.8 something. After rounding off, it would be 1.9 electron volt. Now all of these have work function greater than this, so it cannot be. So as E is less than phi A, E is less than phi B, E is less than phi C, E is less than phi D. All of them are greater. So this photon could not be able to eject electron from any of given metals. Stopping potential for a photoelectron are 5 and 7.5. When photons of frequency 5 into 10 to the power 14 and 7.5 into 10 to the power 14 incident on it, find phi and nu naught. So it is basically an ordinary simultaneous equation will be formed here, and we can solve them. Einstein equation. So here we know that V naught equal to h nu minus nu naught. So case 1, so we will have V naught 1 is equal to h nu 1 minus nu naught, and V naught 2 h nu 2 minus nu naught. So in first equation, nu naught V naught 1, that is 5 is equal to h is h. In fact I am putting it here, and nu 1 is 5 into 10 to the power 14 minus nu naught. Oh, if nu naught is calculated, then we can also find phi, or vice versa. So not a big issue there. From here we can find nu naught. Actually I felt that more unknown values are there, but it is quite known. Oh, one mistake is there. So it will be like this. So no problem, we can do it like this, nu naught, and then this will be taken that way. So actually this part is not required. I think, I don't know whether I have missed something in this question or not, but we can end up the question here only. Minus E5 by value of h. We will use the value of h in electron volts, electron volt second, that is. So it is 4.14 somewhere. You can find it out. H equal to 6.62 into 10 to the power minus 34 joule second. If it is not given in terms of electron volt, still you can find it. So it will be 4 point something. So I know that it is 4.14, or you can divide it into 10 to the power minus 15 also. Electron volt second into 10 to the power minus 15. So now it is in electron volt. So electron is also there. So you can get these electron get cancelled, and now we can divide it. So 5 into 10 to the power 14, it will be divided. So that will be 1.2, I guess, into 10 to the power 14, 15. So it is bringing out a dramatic result. Minus 12 into 10 to the power 14. I have just adjusted the point here, and it is giving negative. So that is what I'm saying, whether I have copied a wrong question, or maybe it was meant for that, which is not possible. So which is not possible. But theoretically we can obtain it, and in the same way you can find it. Same process, just replace this 5 with 7.5, and this 5 into 10 to the power 14 with this 7.5 into 10 to the power 14. So maybe this question would be asked in the exams to check whether you could be able to sort out this problem, or see, because this frequency is negative, it is not possible. But of course, uh, on the basis of a number system, we can calculate it. But this is not possible. It means with this frequency incident photon, we can't get a photoelectron whose stopping potential is 5. That is hypothetical. Numerically, we can find, but that does not exist physically. All right. Find photo energy associated with photon. Okay, in electron volt. So again and again, similar kind of question. You try it of your own and pause the video, do it yourself, and then I'm giving you the solution for this. Hc by lambda, and value of Hc we know. It is in nanometer. So in fact, we know the value of Hc in nanometer, electron volt nanometer, upon lambda 550 nanometer. Cancelled, electron volt will be the answer. So it will be 1242 by 550, 1.1, somewhere close to it, electron volts. Find number of photon emitted per second by a lamp. That's a very good question. Of 2000 watt, radiating light of wavelength 800 nanometer. So we know that power equal to work upon time, but here we'll use energy upon time, and for energy we'll use Hc by lambda, because lambda is given, lambda t, and we have to find, oh, not Hc by lambda, because there are not a single photon is coming, but number of photons are coming. So we can set a formula for n. So n will be equal to p lambda t upon Hc. So p is 2000, lambda is 800 nanometer. I'm not mentioning it here, nanometer. I'll use value of Hc in terms of nanometers. Time per second, that is 1. Hc, whatever, in nanometer. So it was this. I'm directly using it by writing this 1242. So that's all, because now we can easily find it out and see, because okay, one problem is there, because this is in electron volt, so I have to put E also here. All right, otherwise it is electron volt meter, and that will get cancelled. That value of when we put the value of electronic charge, then its unit and volt together form joule, which is in SI unit, so no problem with that. So what I have to do, I have to use the value of E also. So here the value of this one, we have to include electronic charge also. So 1242 into 1.6 into 10 to the power minus 19, and here 2000 into 800, and now we can easily solve it. 16 5s are 1.6, actually 1.6 5s are 8, and double zeros. And what else? If we divide this and this, So this will be 1 point approximately 6, 1.6 something, and when we multiply both of them it is again 800. So 800 into 10 to the power 19, or 8 into 10 to the power 21. Find the Broglie wavelength associated with an electron accelerated at 100 volt. It's a direct question. We know that wavelength associated with an electron is 12.27 angstrom by root of V. So even I'm not solving it. Find wavelength associated with cricket ball of mass 160 gram moving with velocity 40 meter per second. It is the fastest delivered ball ever. So I'm directly applying it. H by mv, we know H 6.62 into 10 to the power minus 34 upon m 160, but it is in gram converted into kg, so we have to upon 1000, so that will go in the numerator, into 40 meter per second. Now I'm shifting 2 decimal places here. I'm making it 1.6, and I'm cancelling one of the zeros from here. So 6.62 into 10 to the power minus 34 upon, alright, right now I'm not doing that, I'm just multiplying, into 10 to the power 3. Now I can shift 3 decimal places here and I can cancel this. So it will be 6.62 upon 6.4 into 10 to the power minus 34. I hope you people could understand this. I have skipped one step here. I have written it 6.4 into 10 to the power 3, and there was another 10 to the power 3, they got cancelled. And now if we divide it, it will be 1.03, I guess, into 10 to the power minus 34 meter. That's a very, very small wavelength associated with it. Alright, a photon of frequency, this incident on a metal surface having phi. Find stopping potential. So V naught equal to, direct formula we can use, H by E nu minus nu naught. Well, they have given this phi. It means I have gone one step further, minus H nu naught by E. This one is better. So here V naught, we have to find V naught, H nu, value of H, because in the denominator there is E, we can put value of H, we have that value. We know the value of H is 6.62 into 10 to the power minus 34, but it is better when we have to divide it with the electron and all that, then it is better to use this value 4.14, which you can find by dividing value of H by E into 10 to the power minus 15. Actually electron volt second, I'm using E as a number here, and nu, this is H. Now nu is 8 into 10 to the power 14, and upon E is E minus H nu naught, it is phi. This is phi, H nu naught is phi. We know that, and its value is 2 electron volt. To E, I am writing E as a number, and in the denominator there is another E. So that's all. It will be 32 and 10 to the power minus 1. So it will be 32 into 10 to the power minus 1 means 3.2 minus 2, that is 1.2 volt. You can find it out. It will be 32, well, 30, yeah, 8 4s are 32, then 3 8 1s are 8, and 3 11 1 33, yeah, of course 33. Actually I have rounded off, so I'm taking only to first decimal place, so it will be 1.3 volt. Next, a beam of monochromatic light of wavelength 750 nanometer is incident on a metal surface phi. this one. So same process we have to follow, same process. Instead of frequency, now we have wavelengths. So you can pause the video, you can try it yourself. And now I hope you people have done it yourself. Now I'm doing it. Hc by E lambda minus phi by E. So Hc, once again, that value Hc, the value of Hc, value of Hc is something about 1.989 into 10 to the power minus 25 voltmeter, joule meter actually, joule meter, and we convert it into electron voltmeter. So it is 1.242. I have done it previously also, so you can see it from there also. Electron voltmeter. It is given in nanometer, so we can convert it into nanometer also. 42 into 10 to the power 3 electron volt nanometer. Alright, so we'll put it here. So V naught, actually this is the rough work. V naught equal to this thing, and this thing I'm putting here. I'm writing it 1242. I have adjusted these 10 to the power 3, I mean 3 zeros here. This is the value of Hc, and E, we have to write it also. It is actually a number associated with this unit, so we have to use it. And wavelength is also there, 750. We not required to convert it because we have used Hc in terms of nanometer, so unit will get cancelled. So 3E, E is required, E is as a number. And now this will get cancelled, it will also get cancelled. But here it will be 1 point approximately 3 or 4, even 5, but that doesn't matter because it is minus 1.5, which is not accepted. But this is what this question is all about. So now, beam of light having two wavelength 4,500 4,000 and 5,000 angstrom incident on a photosensitive plate, phi 1 electron volt, find V naught. So what we will do, we will find energy associated with both E1 and E2. So for E1, Hc by lambda, and Hc, value of Hc, we will find value of Hc in terms of, see, value of Hc is 1.989 into 10 to the power minus 25 joule meter. You can find it by multiplying H and C, and then if you will divide it with charge of an electron, then you will find, you can get this value. And when you convert it into nanometer, you would find this value. And this is actually 1242 electron volt nanometer, and when you convert it into angstrom, one more zero will be there, electron volt angstrom. So this value we'll use here. So Hc is 12420, that's all. E is required, electron volt, and angstrom will get cancelled with value of lambda, which is 4000. Angstrom. If you want, I can write it like this. So 0 0 will also get cancelled. 3 place, 2 place. So 3.0 3.105. No, not this much is not required. 3.1 electron volt is enough. In the same way, all right, so now V naught we can find EV naught is equal to E1 minus phi, E minus phi, but E1 here in this case. E1 is 3.1 minus phi is 1, so EV naught equal to 2.1 electron volt. Electron will get cancelled. V naught equal to 2.1 volt. And in the same way here, Hc by lambda, so 1240 eV angstrom upon 5000 angstrom. Angstrom will get cancelled, and we will find this will also get cancelled. Oh, one thing I missed. Okay, that's why the trouble was there. So 5 2s are 10, 5 4s are, and again 5 4s are, and it will go on. That's enough. 2.4 is enough electron volt, and for stopping potential you can do it yourself. So this question, an electromagnetic wave of wavelength, actually electromagnetic wave of wavelength lambda is incident on photosensitive surface, negligible work function. If photo electron emitted from this surface have de Broglie wavelength lambda 1, prove that lambda equal to 2mc upon h lambda 1 square. So let's see, can we find this or not. Okay, so we know that E equal to phi plus kinetic energy maximum. Here phi is negligible, so E equal to kinetic energy maximum, phi negligible. So E is Hc by lambda equal to Ke maximum. Now we have to find matter wavelength, that is lambda 1, which is h upon, we know, root 2m kinetic energy, which is maximum. So that's all. H upon root 2m kinetic energy maximum is Hc by lambda. That lambda will go in the numerator. H root lambda upon root 2m Hc. Squaring both sides. Why? Just because they have given to prove that way. Cancelled, and that's all. Cross multiplying lambda 1 square 2mc upon h1, h will be there. That's all. The maximum kinetic energy of photoelectron get doubled. Okay. When wavelength of light incident on surface changes from lambda 1 to lambda 2, derive expression for threshold wavelength lambda naught and work function phi. Work function phi. Okay. Okay. So first we will find expression for lambda naught, and afterward for phi, because phi is then Hc by lambda naught. So no problem with that. So given is, we know that E equal to phi plus Ke max. So in first case, it is hc by lambda 1 equal to phi plus ke max. In case 2, it is hc by lambda 2 equal to phi plus twice ke max. So we have to eliminate phi first. No, moreover, phi. We have to eliminate ke first. What we can do, we can multiply this equation by 2. Equation 1 we can multiply by 2, and then what will happen? 2hc by lambda 1 is equal to 2 phi plus 2 ke max, and that's all. I think this is 1 multiplied by 2, and if we subtract them, kinetic energy term will get cancelled. There will be minus phi, which is not a big issue for us, and here hc is common, 1 by lambda 2 minus 2 by lambda 1. So this is not this is something which we were looking for, but let's change the sign. Phi equal to, see, actually it is in that side and I have changed the sign, so inside it sign will get changed, because alright, if I would multiply it with negative sign, negative will come here. Later when negative will go inside, this will become negative, this will become positive. So what I am writing, hc 2 by lambda 1 minus 1 by lambda 2. This is the expression for work function. So second part we have done first. Now we will go for first part. So we know phi is hc by lambda naught, that is hc 2 by lambda 1 minus 1 by lambda 2. hc will get cancelled, and that's all. No need to reciprocate that. 2 by lambda 1. And if you want, then we can do it lambda 1, lambda 2, 2 lambda 2 minus lambda 1. This is equal to 1 by lambda naught. So lambda naught is equal to lambda 1 lambda 2 upon 2 lambda 2 minus lambda 1. Okay, state 3 important properties of photon which describe particle picture of electromagnetic radiation. First, quantized energy. So photon picture says that energy is not energy of electromagnetic waves is not continuous but discrete each photon carries energy h nu. So this is something like a uh, particle type behavior of photon. Second, intensity of electromagnetic waves or electromagnetic radiation depends upon number of photon. Once again, particle type behavior, and 3, photons carry momentum just as particles. So that's all in this video, and these questions are enough for this chapter. So practice these questions again and again. That's all for today, and we'll meet in next video for optics.